Imagine traveling back in time to the year 1800. You expect to find a pre-industrial, primitive society dependent on candles and horses. But when you look closer, you discover technologies that seem impossible for that time. Sophisticated machines that shouldn't exist for another 100 years. Innovations that defy everything you've learned about the timeline of human progress. How is this possible? Were these inventions really created back then? Or are we looking at evidence of something more extraordinary? Today we'll explore documented technologies from the early 19th century that seem completely out of place in time. Prepare to question what you know about the history of technology, because what you're about to discover will challenge your understanding of how humanity has truly evolved. These aren't conspiracy theories or empty speculations. They are documented historical facts that simply don't make sense within the conventional narrative of linear technological progress that we've been taught. The electric battery that shouldn't exist. We begin our journey with one of the most surprising inventions of the year, 1800, the voltaic pile, created by the Italian scientist Alessandro Volta. In March of that year, Volta presented to the Royal Society of London a device that generated continuous electricity through chemical reactions. But here's what makes it truly extraordinary. This technology shouldn't have been possible at that time. Consider the context. In Saracen 1800, atomic theory was still in its infancy. No one fully understood the nature of matter, much less the complexities of chemical reactions at the molecular level. There was no knowledge of electrons, protons, or ions. The periodic table wouldn't be developed for another 69 years. Yet Volta managed to create a device that exploited electrochemical principles with impressive precision. His pile consisted of alternating zinc and copper discs separated by cardboard soaked in brine. When stacked in series, these discs produce measurable and usable electrical current. The elegance of this solution is impressive even by modern standards. Volta not only created the first battery, he established principles that still underpin all modern batteries. 2 different electrodes, an electrolyte, and the conversion of chemical energy into electrical energy. How could someone in the 1800s, without electron microscopes, computers, or modern laboratories, develop technology that remains essentially unchanged in its fundamental conception more than 200 years later? What is even more intriguing is the speed with which this technology was adopted and applied. Within months, scientists across Europe were replicating and improving Volta's design. In 1801, less than a year after the initial presentation, the voltaic pile was being used for electrolysis experiments, leading to the discovery of new chemical elements. This speed of dissemination and application suggests not only individual genius, but a network of technical knowledge and experimental capacity that supposedly should not have existed in that period. Critics may argue that Volta simply had brilliant insight based on Luigi Galvani's experiments with frogs. But this does not fully explain the conceptual leap involved. Galvani observed muscle contractions in frog legs when exposed to different metals. Volta transformed this observation into a functional device that generated consistent and controllable electricity. This leap from biological observation to technological application required a deep understanding of principles that were theoretically unknown at the time. If you're fascinated by these impossible technologies and want to uncover more secrets hidden in history, this is just the beginning. Subscribe to the channel now and activate the bell so you don't miss any revelations. Leave a like to show you want more investigative content like this, and don't forget to click the hyper button below. Your help is essential for us to continue investigating and bringing to light truths forgotten by official history. Together, we will unearth more technological mysteries that challenge everything we know. The Jacquard Programmable Loom. In the same year, 1800, while Volta was revolutionizing the understanding of electricity, Joseph Marie Jacquard in Lyon, France, was completing an invention that many computer historians consider the true predecessor of the modern computer, the Jacquard loom. This was not simply an improved loom. It was a machine that used punched cards to store and execute complex instructions, automatically creating intricate textile patterns. Let's understand the magnitude of this innovation. Jacquard created a system where information was encoded on paper cards through hole patterns. These cards were then mechanically read by the machine, which performed specific operations based on the presence or absence of holes in precise locations. This is programming. This is binary information processing. This is data storage. In 1800, Charles Babbage, who would later design his analytical engines considered precursors to computers, explicitly acknowledged the Jacquard loom as a fundamental inspiration. Ada Lovelace, often credited as the first computer programmer, studied the principles of the Jacquard loom when developing her algorithms for Babbage's analytical engine decades later. But Jacquard got there first, and his technology wasn't theoretical. It was in actual production, transforming the French textile industry. What makes this even more astonishing is the mechanical precision required. The Jacquard loom had to read cards, interpret hole patterns, and execute complex mechanical movements with perfect timing. This demanded precision engineering in metals and wood, at a time when machine tools were still relatively primitive. How did early 19th century artisans manage to manufacture components with tolerances precise enough for this system to function reliably? The conceptual sophistication is equally impressive. Jacquard understood that information could be encoded, physically stored, and mechanically processed. He created what is essentially a programmable external memory system. Different cards produce different patterns, allowing the same machine to create an infinite variety of designs without physical modification of the loom. This is computational thinking before the concept of computing existed. Within decades, their looms were being used throughout Europe and America, producing intricate fabrics that previously required highly skilled weavers working manually for weeks. The technology democratized luxury production and fundamentally altered the global textile economy. But the question remains, how did this concept emerge so fully formed in the 1800s? The Napoleonic optical telegraph network. While we discuss the impossible technologies of the 1800s, we need to talk about something most people don't even know existed: a real-time communication network covering all of France and beyond. Claude Chapp's optical telegraph had been fully operational since 1794, but by 1800 it had expanded into a sophisticated national communication system. This system consisted of towers spaced 10 to 20 kilometers apart, each equipped with movable arms mounted on top. Operators in the towers used telescopes to observe the previous tower in the line and replicate its arm positions, relaying messages across hundreds of kilometers in minutes. Messages could travel from Paris to Lyon, a distance of 400 kilometers, in less than 2 hours. To put this in context, before this technology, the same message would take 3 days on horseback. The optical telegraph not only transmitted messages faster, it operated at speeds that were orders of magnitude greater than any previous communication system in human history. Napoleon Bonaparte immediately recognized the strategic value of this technology. Under his command, the network expanded dramatically. At its peak, there were over 500 optical telegraph stations connecting major French cities and conquered territories. This represented a massive investment in communications infrastructure on a scale that would not be seen again until the electric telegraph decades later. What is truly remarkable is the organizational and technical complexity involved. Each station needed to be precisely positioned for a clear line of sight with adjacent stations. Operators needed to be trained in a sophisticated coding system that allowed for the efficient transmission of complex messages. There were protocols for error checking, for dealing with bad weather conditions, for equipment maintenance. This was not primitive technology. It was a sophisticated communication system that required coordination of engineering, logistics, and human resources on a national scale. Historians often underestimate the importance of this technology because it was quickly superseded by the electric telegraph. But this ignores the fact that in the 1800s, France had a capacity for instantaneous communication across its territory that no other nation possessed. This was an extraordinary technological and military advantage. How was this network planned, built, and maintained with technology from the late 18th and early 19th centuries? The mechanical precision of the signaling arms, the logistical organization, the training of hundreds of operators. All of this represents a level of administrative and technical sophistication that seems anachronistic for the period. The railroad revolution begins prematurely. Although the first public steam railway wasn't inaugurated until 1825, the technological foundations were all present in 1800 in a way that defies conventional understanding. Richard Trevithick had already built the first operational steam locomotive in 1801, just 1 year later, but to build a functional Locomotive in 1801. You need to master advanced metallurgy, pressure engineering, fluid dynamics, and precision mechanics. Consider what's involved in creating a mobile steam engine. You need to build a boiler that can contain steam under high pressure without exploding. This requires a deep understanding of material properties and manufacturing techniques capable of producing consistently high-quality metal. You need to create valves, pistons, and cylinders machined to precise tolerances. Need to understand thermodynamics well enough to optimize efficiency, and all of this needs to be built robust enough to operate under conditions of continuous stress while moving on rails. The rails themselves represent another technological challenge. Cast iron of sufficient quality to support the weight of locomotives was not a readily available commodity. Producing rails required furnaces capable of high temperatures, refining processes to remove impurities, and molding or rolling techniques to create long, uniform pieces, and you needed to produce thousands of these rails to build even a short railway line. Trevithick wasn't working in a modern laboratory with precision tools and industrial materials. He was in Cornwall, England in the early 19th century using technology that supposedly had barely emerged from the pre-industrial era. Yet, his locomotive worked. It pulled wagons loaded with passengers and cargo. It proved that steam-powered rail transport was viable. Technical knowledge required for this achievement is astounding. Trevithick had to understand that high-pressure steam was more efficient than the low-pressure steam used in stationary machines. He had to design a boiler strong and light enough to be mobile. He had to solve the problem of effectively transmitting power from the piston to the wheels. Each of these challenges required profound engineering insight. Within 2 decades, railways were spreading across England. In 1830, there were regular passenger lines. In 1840, the railroad was transforming the global economy, but the speed of this transformation was only possible if the fundamental technical knowledge was already widely available much earlier than is generally recognized. Gas lighting and advanced urban infrastructure. In the 1800s, London and some other European cities were already experimenting with gas street lighting. William Murdoch had illuminated the Bolton and Watt foundry in Birmingham with coal gas in 1792. By the 1800s, this technology was beginning to expand into public lighting, but consider what this really means. Creating urban gas distribution infrastructure. You need to install underground pipeline networks throughout entire cities. These pipelines need to be airtight to prevent dangerous leaks. You need to build gas production facilities that heat coal in a controlled environment to produce fuel gas. You need to develop burners that produce consistent and safe light. You need to create pressure regulators to ensure uniform supply through extensive networks. And you need to do all this with early 19th century technology. The scale of civil engineering involved is impressive. Excavating streets to install pipelines, coordinating installation across multiple properties, connecting individual buildings to the central system. This requires not only technical capacity, but also sophisticated administrative and legal structures. Someone needs to plan the routes, negotiate rights of way, establish safety standards, train workers. This is complex public utility infrastructure emerging decades before the supposedly necessary era of advanced industrialization and modern bureaucratic organization. The safety aspect is particularly intriguing. Coal gas is toxic and flammable. Leaks can cause dangerous situations, yet engineers in the early 19th century developed systems safe enough to be installed in densely populated urban areas. They created safety valves, developed leak detection methods, and established maintenance protocols. How did they acquire this knowledge without the extensive testing and iterative development we associate with new technologies? Within 3 decades, major European and American cities had extensive gas lighting networks. Streets that had been dark since the dawn of human civilization were now illuminated at night. This fundamentally transformed urban life, but the speed of this transformation suggests that technical capabilities were far more advanced much earlier than conventional historical narratives acknowledge. Complex mechanical calculating machines. The history of computing generally begins with Charles Babbage and his difference engine in the 1820s, but mechanical calculating devices existed long before, and by the 1800s they were already surprisingly sophisticated. The Pascaline, invented by Blaise Pascal in 1642, could perform addition and subtraction. Leibniz's calculator from 1674 could multiply and divide. These were not theoretical concepts, they were functional machines. But what makes their existence so intriguing is the extreme mechanical precision required to manufacture them. A mechanical calculator needs gears machined to tolerances of fractions of a millimeter. Any play or imprecision results in calculation errors. The digit carry mechanisms, where a digit reaching 10 increments the next digit, require particularly delicate engineering. How did craftsmen of the 17th and 18th centuries managed to create such precise components using hand tools? By the 1800s, these machines were becoming more complex and beginning to be produced in larger quantities. Thomas de Colmar's arithmometer, presented in 1820, was the first mass-produced mechanical calculator, but its development depended on manufacturing techniques that already existed in the 1800s. There were workshops capable of producing mechanical components with sufficient precision for reliable calculation. The mathematical knowledge incorporated into these machines is also remarkable. Designers needed a deep understanding of arithmetic, positional number systems, and how abstract mathematical operations could be performed through physical mechanical movements. They were essentially creating algorithms in metal before the concept of a computational algorithm existed. Think about the conceptual leap involved, transforming mathematics, an abstract mental activity, into a physical mechanical process. This requires the kind of thinking we usually associate with modern computer science. How did this thinking emerge so early? Some historians argue that these machines were expensive curiosities with limited practical impact, but this underestimates their importance. They proved that calculation could be automated. They established principles that Babbage and others would expand upon, and they demonstrated that artisans of that period possessed extraordinary technical skills. Medical advances and scientific instrumentation. The 1800s also marked medical and scientific developments that seem premature for the time. Edward Jenner's smallpox vaccination, developed in 1796, was beginning to be widely adopted in 1800, but consider what this represents. The understanding that exposure to a related but less dangerous disease could confer immunity to a deadly disease. This is sophisticated immunological thinking, decades before germ theory was established. Jenner did not understand underlying biological mechanisms. Immunology as a science would not exist for another century, yet he developed an effective medical procedure based on careful observation and experimentation. As is often the case with surprising early technologies, practice preceded theoretical understanding. This raises the question, how many other effective techniques existed based on empirical knowledge without explanatory theory? Scientific instrumentation was also advancing rapidly. Microscopes in the 1800s could achieve magnifications of several hundred times with reasonable clarity. This required precisely polished lenses and sophisticated lighting systems. Telescopes were being built with ever larger apertures and complex equatorial mounts for precise tracking of celestial objects. William Herschel had discovered Uranus in 1781 using a telescope he built himself. By 1900, astronomers were mapping skies with increasing detail, discovering asteroids, and refining their understanding of the solar system. The manufacture of these precise instruments is an art in itself. Creating a large, perfectly curved telescope mirror using hand polishing techniques is extremely difficult. Manufacturing microscope lenses corrected for chromatic aberrations requires a deep understanding of optics and exceptional craftsmanship. How were these levels of precision achieved? Electrostatic and electromagnetic instruments were also proliferating after Volta's demonstration of the electric battery. Scientists rapidly developed voltmeters, galvanometers, and other devices to measure and manipulate electricity. Alessandro Volta, Luigi Galvani, and others were conducting experiments that mapped electrical phenomena with increasing precision. This flourishing of scientific instrumentation in the early 19th century represents the technological infrastructure that enabled the explosion of scientific discoveries that followed. But this infrastructure had to be built first, using knowledge and skills that seem remarkably advanced for the period. Advanced manufacturing and metallurgy techniques. Underlying all the technologies we've discussed is a crucial foundation, the ability to work metal with precision. The machine tools that enabled the Industrial Revolution were being developed and refined in the late 18th and early 19th centuries. Henry Maudslay invented the precision threading lathe in 1797. By 1900, he and others were continuing to refine machining techniques. Maudslay's importance cannot be underestimated. His lathe allowed for the creation of screw threads with precision and standardization never before possible. This may seem like a minor technical detail, but it is absolutely fundamental. Standardized screws mean interchangeable components. Interchangeable components mean that machines can be easily repaired and mass-produced. Without this, each machine would be a unique handcrafted creation. The ability to machine metal with precision also allowed for the creation of better tools, which in turn allowed for greater precision in a feedback loop that rapidly accelerated technological development. Metallurgical processes were also advancing. Steel production was improving in quality and decreasing in cost. Techniques for casting large and complex parts were being developed. Understanding of how different heat treatments affected metal properties was growing. Knowledge about alloys was expanding. All of this seems like normal technological progress in retrospect, but when you consider that it was happening simultaneously with all the other innovations we discussed, the picture that emerges is one of an extraordinarily concentrated technological explosion. In the space of a few decades around the 1800s, humanity developed usable electricity, mechanical programming, long-distance communication, steam transport, city lighting, automated calculation, and precision manufacturing. How did all this happen at the same time? One explanation is that these developments were interdependent. Better tools allowed for the construction of better machines. Better machines expanded what was possible to build. Knowledge circulated ever more rapidly among scientists and inventors. Scientific societies, publications, and international correspondence created networks for sharing information. But even recognizing these synergies, the speed and scale of the transformation are impressive. It's as if humanity has reached a technological tipping point where progress has begun to accelerate exponentially. Knowledge networks and technology transfer. One often overlooked aspect of these early technologies is how quickly they spread geographically. When Volta announced his electric battery in 1800, scientists in London, Paris, Berlin, and other European cities were replicating his experiments within months. When Jacquard perfected his programmable loom, the technology was adopted across Europe and America within decades. This speed of dissemination suggests more sophisticated communication and knowledge transfer networks than we generally imagine for that period. Scientific academies existed in major cities. Scientific journals published discoveries and innovations. Correspondence between scientists and inventors was extensive. Prototypes and models traveled between countries. There was already an international community of technological and scientific practice. But how did these networks function in practice? Letters took weeks or months to travel between countries. Technical drawings needed to be detailed enough to allow replication without video or photography. Tacit knowledge, the kind of practical knowledge that comes from hands-on experience, had to be transmitted through text or by the travel of qualified individuals. There is evidence of industrial espionage and deliberate technology transfer. Skilled workers were recruited to carry knowledge from one country to another. Governments sent agents to learn about foreign innovations. Entrepreneurs bought patent rights or simply copied designs. This environment created competitive pressure that accelerated innovation. The mobility of skilled artisans and engineers was also an important factor. People with valuable technical skills could find employment in different countries. This circulation of human expertise was a crucial form of technology transfer. A Swiss watchmaker working in England, an English engineer consulting in France, a German metallurgist immigrating to America. Each brought specialized knowledge. The role of universities and technical schools was growing. France established the École Polytechnique in 1794, specifically to train engineers. Other nations followed with similar institutions. These schools not only taught scientific principles, but also practical engineering techniques. They created an educated workforce capable of implementing and improving technologies. All this suggests that 1800 was not the starting point of the technological revolution, but a moment in an already mature system of knowledge development and dissemination. The foundations were laid decades earlier, revisiting our understanding of technological progress. So what should we conclude about these seemingly impossible technologies of the 1800s? Were they truly impossible? Or is our understanding of technological progression oversimplified? The standard historical narrative presents technological development as a gradual and linear process. Each Innovation builds upon the previous one in an orderly fashion, but when we examine it in detail, we see that reality is more complex. There are sudden leaps, independent parallel developments, empirical knowledge preceding theoretical understanding, and periods of rapid acceleration. The 1800s appear as one of these acceleration points. Multiple lines of technological development converged. Knowledge that had been accumulating in different domains began to connect and reinforce each other. Improved manufacturing capabilities allowed for the construction of more sophisticated machines. Improved communication accelerated the sharing of ideas. Economic incentives rewarded innovation. It is also important to consider what we don't know about early technologies. Historical records are incomplete. Many technical developments were not documented because they were considered proprietary commercial knowledge. Craft skills were often transmitted orally and by demonstration, not in writing. It is possible that technical capabilities in certain domains were more advanced than surviving records suggest. There is also the question of survivorship bias. Technologies and artifacts that have survived to our time may not be representative of what existed. Perhaps there were even more advanced experiments and prototypes that have been lost. Or perhaps the cases we know of were exceptional and not typical. We must also acknowledge the role of chance and individual genius. People like Volta, Jacquard, Trevithick, and others were exceptionally talented individuals who made intellectual connections that others did not see. The history of technology is not only a product of abstract historical forces, but also of the creativity and insight of specific people. Finally, we must be open to revising our understanding as new evidence emerges. The history of technology is an active field of research. Historians continue to uncover documents, reevaluate artifacts, and refine chronologies. What we know about the 1800s today may be modified by future discoveries. Ultimately, these early technologies remind us that our ancestors were as intelligent and creative as we are. They worked with different tools and knowledge, but they possessed the fundamental human capacity to observe, experiment, innovate, and solve problems. The technologies of the 1900s were not impossible. They were a testament to human ingenuity applied during a time of extraordinary historical transformation. If this video expanded your understanding of the technological capabilities of our ancestors and showed you that history is more fascinating than we imagine. Please like it now to support this type of in-depth historical investigation. Subscribe to the channel for more content that challenges conventional narratives and reveals forgotten truths. The video currently playing on your screen will perfectly complement everything you've discovered here. Be sure to watch it. Thank you so much for taking the time to explore with us the technological wonders hidden in history. Until the next extraordinary discovery.